Welcome back. In Chapter 3, we're going to start looking at optimization. That's one of the strengths of calculus. It allows us to find maximum and minimum values for functions. And in this section, we're going to start introducing some definitions and some important theorems. To begin with, let's start by defining what do we mean by absolute maximum and absolute minimum values for a function. So we've got some function f, and it's defined on an interval I. And I'm not specifying now whether that interval I is the entire domain or just part of the domain, but we've got some interval, and there's an x value in that interval. And if the y value for our function at c happens to be smaller than all the other y values in that interval, then that y value is the absolute minimum on that interval, or it is the minimum value. And same thing if we're thinking about f of c and looking at that y value, if it's bigger than all the y values in the interval, then f of c is the maximum, or the absolute maximum for the function on our interval. Now, again, it's possible that we might have a function that has both. Maybe we've got a maximum and a minimum. Maybe we only have one thing of just a maximum or just a minimum. Maybe we've got none of the above. And maximums and minimums don't have to occur only once. If you have a maximum, maybe it occurs multiple times. So some examples of these things, if you're thinking about something like the equation of a half circle, that's something where we have a maximum value. Just to make my life easy, I'll make it a half circle with a radius of 1. So you have a maximum value here. The maximum y value happens to be 1, and it happens exactly once. But you also have the minimum y value being 0, and that happens in two different places. So maximum and minimum, they could exist in multiple locations. You could also think about things where maybe you don't have a max and don't have a minimum. That might be something like over all the real numbers, the equation y equals x. So looking at all the x values, there isn't an x value where the y value on the line is the biggest, not for all the real numbers. And same thing, there's no point on the line where the y value is the smallest. So something like y equals x over all the real numbers has no extrema at all. We have this little half circle, has a maximum and also has a minimum. We could even have things where maybe you just have one but not the other. So something like our friend the absolute value function, that has a minimum value of 0, and that happens when x is 0, but it doesn't have a maximum value, and that's because there is no largest y value for that function. Of course, one big obvious thing is if we've got a maximum or a minimum happening at x equals c, then x equals c had better be part of our domain. You can't have a maximum where you don't have a function. You can't have a minimum where you don't have a function. So if we're taking a look at this problem, here is basically our old friend, the parabola y equals x squared. But I have it on three different intervals. The first one is looking at the interval of all the real numbers. And if I were looking at this parabola for all the real numbers, I would say that we definitely have a minimum. But we don't happen to have a maximum. And that's very true that there's no largest y value if we're thinking about it on the interval of all real numbers. If I'm thinking about just on the interval from -1 to 3, we still have a minimum value of 0. And we also now have a maximum value. It looks like it's going from -1 to 3, which means my maximum value would be 9. So just as a reminder, the equation we're talking about is y equals x squared. So when x is 3, the y value would be 9. This was a closed interval, including the endpoint at -1 and including the endpoint at 3. Similar sort of interval, but this one an open one. So you'll notice if I zoom in, instead of filled in circles at 1 and at 3, I have little hollow circles at 1 and at 3 to show that the points 3 and -1 are not being included. X being 0 definitely still is, so we still have our minimum of 0 at x is 0. But in this case, we do not have a maximum. The y values are getting larger and larger and larger. The largest y value that you'd like to point to would be 9, but unfortunately, that happens when x equals 3, and 3 is not being included as part of this interval. So we can't have a maximum when x is 3 because 3 is not part of the interval. So there is no maximum. There's lots of values that are close to 9, so 8.97 and 8.98 and 8.9995 and all these other larger values, but there is no largest value on that interval, unfortunately. If we're looking at this one now, going from -3 to 3, and this is closed brackets, so we're including both endpoints. As always, as we've had for all of these, we've had a minimum of 0 at x equals 0. And in this case, we'll have the maximum value of 9 showing up in 2 places. So this is also something to be aware of or think about as we're solving these questions. Is that there's 2 sort of related things that we can talk about when we're talking about maxes and mins. We can talk about the value, and that's the y value. Is it a maximum value or a minimum value? And then there's also the when or where does this happen? That's the x value. So sort of 2 things to mention here, that we have a maximum value of 9, and also where does that maximum happen? Happens at 3 and also happens at -3. So one big theorem, a nice important one, is the extreme value theorem, which guarantees the existence of a maximum and also a minimum, provided that we've got this little side condition met. As long as we have a function that's continuous on a closed interval, so that's the important part. 2 things we need. Number 1, the function needs to be continuous. Doesn't have to be continuous everywhere, but it needs to be continuous on the interval. And the other thing is the interval needs to be a closed one, not an open one. And so you can sort of see that in action, actually, in the last part. When we had an interval that was open from -1 to 3, not including it, we had a minimum, but we didn't have a maximum. There was no guarantee that you'd have both. But when we had a closed interval from -1 to 3, including both endpoints, then you're guaranteed by the extreme value theorem that since our function is nice and continuous, you'll have a minimum and also a maximum. So we've got a guarantee via the extreme value theorem. Now, a couple of things just to mention about the theorem. The theorem can, like I say, fail for you. If the function is not continuous, then the extreme value theorem does not apply. If we're not talking about a closed interval, then the extreme value theorem does not apply. It's possible you might still have maximum and minimum values. It's just not necessarily courtesy of the extreme value theorem. So, for example, something like this function f of x, it's doing 2 different things. It has a y value of -1 when we're 0 and less, and it has a y value of 1 when we're larger than 0. So if you were graphing that out, it would look a little something like this. And so for sure it's discontinuous when x is equal to 0. It's definitely discontinuous on the closed interval from -5 to 5. But it's also very obvious that we do have a maximum value and a minimum value. The maximum value is 1, and that happens for all the x values that are larger than 0 up to 5. And we've got a minimum value of -1, and that happens for all the x values that are 0 and smaller all the way down to -5. So you can still have maximum and minimum values. What the extreme value theorem does for us is give us a guarantee that we'll have one of each. Now, there is another kind of extremum to talk about, and that's relative extrema. So absolute extrema, these were extreme values that were larger than all the y values in the interval. But here for a relative extrema, we're saying we're going to first off talk about our function being defined not just on any old interval, but rather on an open interval containing c. And if you've got x equals c inside that open interval, and if f of x is bigger than all the y, f of c is bigger than all the y values in that interval, then you can say that f has a relative maximum when x is equal to c. And if y is the y value at c is smaller than all the y values in that interval, then f has a relative minimum. So this is not necessarily the biggest or smallest of the entire graph. It's just the biggest or smallest y value in that interval. So just to give you a little doodle as an example here, suppose I've got a function that looks a little something like this. I could say, for example, that inside this little interval going from here to here, that you definitely do have a maximum value at that point. That would be the largest y value that you've got going in that interval. So you do have a maximum. It's not the largest y value for the entire graph, though. So that's not an absolute maximum. It's a relative maximum. And similarly, if I'm thinking about, let's say, in this little interval here, I have a smallest y value in that little interval, that would also be a relative minimum. It's not the smallest y value for the entire graph, but it's definitely the smallest compared to everything around it. That's the idea about a local or a relative minimum or a local or relative maximum. They're smaller than or larger than the things in their immediate vicinity, but not necessarily the biggest thing overall. So a couple little bits of commentary here. First thing, of course, drawing attention to the open interval. Maybe the open interval is the entire domain, maybe not. But one thing is definitely true is if we're talking about a point being inside of an open interval, that means that that point is not going to be the end point. So when we're talking about an open interval, we're talking about an interval going from some point A to some point B, not including either endpoints. So if x equals c is inside this interval somewhere, it's not going to be the endpoints because the endpoints are not included as part of that interval. So automatically that means that if we're talking about functions that go on and stop at a point, for example, something like our square rooting function, square root of x, that is defined from all the values 0 and larger. This is not something contained inside of an open interval. So that means that would not be considered a relative minimum, even though it is the smallest y value on the entire graph. Even though it is an absolute minimum, it is not a relative minimum, because to be a relative minimum, you need to be a point inside of an open interval, and you have to be a point that's the smallest y value for all the y values inside that open interval. So if you're not inside of an open interval, in other words, if you're an endpoint, you cannot be a relative anything, relative max or relative min. Of course, you can be a relative something and also be an absolute. So for example, something like our friend the parabola y equals x squared, I can say for sure that the point 0, 0, that definitely we've got an absolute minimum value of 0 happening when x is equal to 0. That is definitely the smallest y value for the entire parabola y equals x squared. But if you're just thinking about the interval around that point, it's also the smallest y value in that interval, which means that we definitely also could consider that to be the relative minimum. So you can be a relative minimum and also an absolute minimum at the same time. And in fact, that definitely can happen. Okay, so one little thing to introduce before the break, and that's the idea of a critical number. This is going to come back in several places in this chapter. So we're introducing it now, but we're going to talk a lot more about them in the future. When we're referring to a critical number, we're referring to an x value where either the derivative is equal to 0 or the derivative doesn't exist. So one of two things. If f prime of c is 0 or if f prime of c does not exist, then you could say that c is a critical number. And then that point, c f of c, you would call that a critical point. So that's something that's going to be important later on for us locating maximum and minimum values. Part of our work will involve finding critical numbers. And part of it is because of this relatively important theorem, which is that if you have a relative extremum, then you are guaranteed that that point must be a critical number. So if I tell you I've got a function and there's a relative extremum when x is equal to 3, then I know that 3 is a critical number, which means either f prime of 3 is equal to 0 or f prime of 3 is undefined. We have to be careful here. This is a statement that really only goes in one direction. If you have an extremum, then you'll have that being a critical number. The reverse is not true. If I give you a critical number, that's not necessarily a point where that's going to have a relative extremum. A good example of that is this y equals cube root of x function. If you were looking at the derivative of cube root of x, which is x to the 1/3, you'd find that the derivative is 1/3 x to the negative 2/3, or 1/3 x to the 2/3. And for sure, you can find that f prime is never equal to 0, because this fraction couldn't be equal to 0, because fractions are only ever equal to 0 when the numerator is 0. And here the numerator is always 1. However, we can say that f prime is undefined at x equals 0. Now, so that means 0 is a critical number. And unfortunately, though, we don't have a relative anything happening on our graph when x is 0, and that's because we know what the graph of x cubed looks like. At y equals x cubed, y equals cube root of x rather, at x equals 0, we don't have a maximum. We also don't have a minimum. We have a f prime being undefined because at that point we've got a vertical tangent line, but there's no max, there's no min, even though we happen to have a critical number. So we have to be careful here. If you have an extreme value, then that happens at a critical number, but the reverse is not necessarily true. If you have a critical number, it may or may not be the location of an extreme value.